Hello, sir. Hello. Sir, can you hear me? Hello, sir.
Hello.
Sir, can you start this live stream, YouTube live stream? I
Okay.
can't start from my end. So there is a custom live streaming option.
Custom live stream. Yes.
Yeah, yeah.
Shall I close the YouTube?
Yeah, I guess it's live streaming.
Are you able to see the screen?
Yes, we can see.
Okay. Fine. We'll start at 5:05.
Yeah, yeah, sure.
Soumya, I will be starting.
Yeah, okay, sir. Yeah, all right.
Yeah. Good evening in India, and if you are abroad somewhere, I don't know what time slot it is. So let me begin with this lecture on calculus and overview. I will stop my video because I want to share my screen rather than showing my face to you. So I'll stop the video and we'll have a look at the screen. Right. It's interesting. Um, when you want to offer something free, uh, people want to grab it and then they forget about it. So we had around 249 registrations online, and as the count shows, we have 22 participants online. So 10% have joined, not bad probably. So anyway, so let us begin. So let me begin with uh, something that is my sort of, in a sense, trademark. I will start with the problem. So here is a problem. Please have a look at the screen and so what the video shows is water is being filled in a glass which is a cylindrical shape. So and a graph is plotted against the water is filling at a constant rate. So, and a graph is drawn of the height versus the time. So time versus the height, the graph, and that is a straight line. Okay, as the graph is shown in the video here. So naturally the question arises, how does the software or whichever way it is done, the graph is a straight line. So can we justify it mathematically? So that is one question we'd like to find an answer to. And can you calculate the volume when the jug is half full? When it is half full, how much is the water inside? Or what is the, if the shape of the glass Okay, let me just pull it back and hold it somewhere. So supposing the glass has some kind of a stone inside. So how much will be the water in the glass? So volume of the water in the jug, we want to find out when it is some kind of a stone lying inside the glass. So one would like to find answers to these kind of questions. They're very simple questions which are answered by our topic called calculus, which is the topic for the day. So we're going to look at an overview of this subject called calculus. So let me just say that the word calculus comes from the Latin meaning small stone, and it is like understanding something by looking at small pieces. And so differential calculus cuts something into small pieces and observes what is the change, how things are changing. And integral calculus joins small pieces together to find out how much there is overall. So this is, sorry. So this is, in a nutshell, the two different parts of calculus. One is called differential calculus, and other is called integral calculus. So we'll be looking at both of these. So let me give you a summary of what I want to do today in this lecture. We'll be looking at calculus. Let me just for a minute. Right. Yeah. So the topic is calculus. So as I said, it has two parts. One is differential calculus, and the other is integral calculus. So we'll be looking at a bit of history of differential calculus, and also looking at a bit of history of integral calculus, and then see how this lead to the work of Sir Isaac Newton and Gottfried Leibniz. So we'll describe their work a bit, and then from there on, we'll look at the modern version of calculus. What is differential calculus, the big picture, integral calculus, the big picture, and then the two coming together in what is called the fundamental theorem of calculus. So this is going to be roughly the scenario for the today's talk. So let me begin with the first part, that is the history of differential calculus. So the main problems discussed are historically are what is a tangent and what is velocity or intensity at a given instant, what is the speed of an object moving. So these are the two main problems which were considered historically. Intuitively, a tangent is a line that touches something, that touches a curve. Okay. So what does that mean? That making that precise, it has a lot of history to it. Euclid in his book 3 defines what is he calls as a tangent to a circle. So he says that the straight line drawn at right angles to the diameter of a circle from its extremity will fall outside the circle and into the space between the straight line and the circumference. Another straight line cannot be interposed. That means given a point, essentially it says that given a point on the circle, if you join it with the center, then there is one and only one line which can be drawn through the point on the circle, which is perpendicular to the radius. So that is what essentially he means by tangent to a circle. Right. The Apollonius was the next one who extended these ideas to conics. So from circle, he went to conics. And essentially, the same idea of touching the line, but he says that it is a straight line drawn through the extremity of the diameter of the any conic parallel to the ordinates of the diameter. The straight line will touch the conic, and no other straight line can fall in between the conic and that line. So Archimedes was the next one in antiquity. Antiquity is before Christ. So then he looked at what is called Archimedean spiral, is the curve traced out by a point advancing uniformly on a line which turns uniformly around a fixed point. So you imagine a circle moving with a uniform speed and take a point. Okay, so that is Archimedean spiral. So Archimedes talks in his work about tangents, but he never defines precisely what is a tangent. Apparently, once again, he means by a tangent a straight line which meets the spiral at a one point, but does not cross it there. Okay, the tangent meets the curve at only one point, but nowhere else in the vicinity. So in a neighborhood, it doesn't cross it again. So essentially touching, that is how he's trying to capture the idea of touching. And by then there was a method of exhaustion proposed in the Greek mathematics, which is a precursor to the concept of limit. And we will use that later. We'll come to that again later on. So he used something called this. Okay. So when we talk about history of integration, right. So this is antiquity, and then comes on the scene Descartes. Descartes on 1637, he looked at idea of same tangents, but he looked at from the point of view of normals. He is seeking to draw a normal to a curve, that is to say, a perpendicular to a tangent at a point of contact. So he defines what he calls as a normal, and he tries to give expressions for the same. So he looked at purely algebraic curves, functions which are given by algebraic expressions, and he was able to give purely algebraic methods of finding these normals and tangents. By the way, he did not have a general idea of handling the coincidental roots. By then, algebra had not developed that much. There was a mathematician around the same time called Jan Houdet, who gave a very nice method of finding this geometric method of finding these tangents. For example, if this is the curve y square equal to x, and you want to draw a tangent at a point C. So he said that look at any circle which is crossing this y equal to square root of x, or that curve, it will cross at 2 points. Let those 2 points be C and E. So if those 2 points are C and E, then drop the perpendicular, you get M and N. Okay. So he said find an expression. So find an expression for O n in terms of OM and Mn. So algebraic expression, and then put the expression for Mn to be equal to 0. Intuitively, that just means that you try to, because the distance is a linear function, later on we will realize it is a continuous function. So putting it equal to 0 means dragging this point C to E. So that can be done in a software called GeoGebra very nicely. So let me probably show you that, how that is possible. in the software. This is only a way of illustrating some things which you can do. So here is a point E. So if we move this point E, okay, and so that this Mn becomes 0, then this point becomes the normal to the circle as well as to the tangent. So the line there, perpendicular line, will be the tangent to that curve also. Okay, so that is implicitly there is a concept of limit and continuity coming into picture very implicitly, very naively it is there. So then came Fermat on the scene in 1629. He looked at the problem of finding tangents and the idea of a tangent. He looked at, in some sense, there is a beginning of infinitesimal calculus hidden in his work, and he could draw tangents to curves which are not necessarily algebraic. So the idea of tangent to as a limiting position of a secant when two with the curve tend to fall together, this idea picked up very slowly, and it became difficult to accept this idea. But by the 17th century, this sort of started getting accepted, and there were mathematicians who contributed in the development of differential calculus, namely basically tangent, and some of them were Persone de Roberval and French, and then Rene Francis Suicide. These are all French people, and then Houdet and John Wallis and the British mathematician Isaac Barrow. So these people contributed, and finally it resulted in the work of Leibniz. So I have given you a very brief history of calculus till Leibniz. We'll describe the work of Leibniz and Newton slightly in detail. Okay, right. There was another parallel problem of what is called the speed of a moving body at a given instant, in instantaneous speed. That was raised by Zeno in his paradox. He says an arrow is fired at a target, and assume that the time consists of a collection of durationless instants. That at every instant an arrow occupies some place it possesses a particular location, but at that particular instant the arrow is not moving. So there is a sort of dichotomy, there is a paradox. At a particular instant that the arrow is stationary, but if you look at the overall picture, it is moving and it hits the target. So that sort of raises a lot of sort of what is it? This is what is called a paradox. There was no concept of instantaneous movement which was available. So this is Greek, and then later on a philosopher by the name in the Matron College of Oxford called Nicole Orsame, he gave the idea of something called an average kind of a thing, right? So V0 and Vt divided by 2 times t. So that is the idea of average things he gave. Nothing much was looked into this idea of instantaneous speed till Galileo came on the scene in 17th century. In 17th century, Galileo looked at moving bodies and speeds, and he gave some rules for the same. Later on, these works were more sort of formalized by the works of Newton. Okay. Can everybody switch off their mics, please? Those who have come recently. Your voices are coming over. Please switch off your mics. All participants, please keep switched on, switched off. All right. So this was the two problems historically. One was the idea of a tangent, and the other idea of what is the instantaneous speed occupied a lot of mathematicians. And finally, we come to the work of Newton and Leibniz. We will describe that a bit later. Let us look for the time being on the integration part. So basically, integration in antiquity meant calculating areas and volumes of objects. So the persons or the philosophers who contributed were Antiphon, Eudoxus, Euclid, and Archimedes. See, my idea of giving you a bit of history is that we should be talking about history in our lectures also, in our school, in our college, because that gives the perspective to the students that how much time it has taken for somebody, for some idea to evolve, how people have struggled with ideas, and those ideas have evolved over time. So if a student finds some idea difficult to comprehend, shouldn't be surprised because the ideas take time to crystallize. Okay. So let us look at briefly these things a bit. Antiphon's main idea was something called the method of exhaustion. He proposed that, and he used to find for polygons approximate area and close by polygons and so on. He did not formulate his things very rigorously. Eudoxus, this method of exhaustion, he perfected that a bit more, and which was later on used by Archimedes to find various formulas of volumes of solids. And that was the beginning of, you can say, algebra. But he didn't have the algebraic, beginning of integral calculus. But he did not have the remarkable thing is, of course, before Archimedes or even many years later, the notion of a function or algebra numbers were not available. Still, they could do many wonderful things. So here is the principle of exhaustion. You can see the concept of limit embedded in it. Given two unequal magnitudes, from the greater of which is subtracted a magnitude larger than its half, and from the remainder a magnitude greater than the half removed, then after a finite number of steps of such operations, a quantity is reached with a magnitude less than any of the smaller magnitudes given. So basically it says that given a, you can go on removing something more than half of the remaining more than half, and what you will be left with will be very, very small, and that small is you can prescribe it beforehand. So that is the idea of a limit is embedded in that. So using this principle of exhaustion, Archimedes was able to find, prove these theorems, which we don't unfortunately do it in our geometry books, that given any circle and any real number absolute greater than 0, there exists a polygon inside it, so that the area of the circle minus the polygon is small. So what we are doing is we are approximating the area of the circle by the area of the polygon. And that is what Archimedes did when he defined what is the number pi. He didn't define it, rather he sort of found it that you take a circle, unit circle of unit radius, its area will be a number. To find out that number approximately, you inscribe a equilateral triangle and go on increasing the number of sides. You'll get a better and better approximation for the area of the circle. There is a very nice applet that in GeoGebra that you can make to say that. So this is radius is 1. This is a circle of unit radius, and you can see the value of the triangle. Area of the triangle is 1.299. So as you increase, the value changes, and you can see as I keep on increasing, even up to approximately around 300, the 3.141. That is the area of that much sided n-gon inside. So that is how basically Archimedes did that. And with these ideas, he could get an approximation that S is the area of the circle. If you take the inscribed n-gons In and circumscribed n-gons as Cn, then because n-gons inside, they are all rectilinear figures, so their areas can be found out. So the area of the inside one at third or fourth stage, I think the third stage is 222 by 71, whereas the outside one is 22 by 7. So the area of the circle lies between these two. And because of that, all our school books take the area of the unit circle to be 22 by 7. It is not equal to, it is approximately equal to 22 by 7, because it is much bigger than S. So, and whether these approximations become better or not, this was finally done in 1842 by defining what is the completeness property of real numbers. And that we'll again see later on, which says that every monotonically increasing sequence of real numbers that is bounded above is convergent. So this requires the concept of sequences, increasing sequences, and limits. That was not known to Archimedes. This is just I'm telling you because some of you or many of you or most of you already know what is the concept of a limit. So this is Archimedes' way of trying to approximate and find out the limit, the area of the unit circle, which they called it as pi. Okay, so let us just summarize the works of Greek mathematicians. They did not have the concept of real numbers. They use only magnitudes for numbers. It was later on done by Dedekind and Cantor in 1872, much later, about 2000 years later than Archimedes. But they were rigorous, and their formulas were derived from stated axioms, and they sort of avoided successfully using the idea of limits, and they could find out particular areas and volumes, but no general methods were given. Okay, so let us come to the works of Isaac Newton and Leibniz. These were the mathematicians in the 18th century who sort of, in a way, proposed some kind of theories on differential and integral calculus. The main contributors before Leibniz and Newton were Stephen, Kepler, Cavalieri. He gave a very good way of finding integrals. Of course, Fermat, the famous Fermat, worked on these things. Gregory, we have the trigonometry series also, John Wallis, Christian Huygens, the physicist, and this is slightly unknown, Pietro Mengoli, and then of course Newton and Leibniz. So let me just say a few words about, I'll skip Kepler and others because we don't have time. So let us come to the works of Newton and Leibniz. Both of them propose independently what we call as differential and integral calculus. And most of the work given by Newton was not published till Leibniz published his work, and then it was a controversy about it. So Newton came to consider power series by looking at the binomial theorem and trying to generalize it. So that is Newton on calculus. Newton thought of variable x as motion. He called as fluents with respect to time, and would call its derivative as x dot, that is the fluxion, the rate of change. Infinitesimals were written as x plus x dot o, and he solved extremal minimum maximum problems about and called about the curvatures and areas. But he was probably aware that the infinitesimal concept that he is proposing is not very rigorous. So, and there may be a lot of criticism about it. So he did not publish his work for quite some time. Leibniz, on the other hand, took a more discrete approach, like saying that an minus a1 is add and subtract terms. So that kind of approach he took. He wrote down the small differences as dx and summation of dx is equal to x. Found differentiation rules for the product in his own way, and fundamental theorem of calculus was obvious to him. What is the fundamental theorem of calculus? We'll see it a bit later on. Arithmetic quadrature of the circle, the series expansion for pi, he could find it. And Newton and Leibniz both were aware of their shortcomings, that their ideas have merit, but they are not very precise. So this, after Leibniz published his work, there was a bitter controversy between Isaac Newton and Leibniz, saying Newton saying that I had done it earlier and so on. I won't go into the controversy, but it's interesting to read nowadays on the internet what is that controversy about. Newton found the results first, but Leibniz published first. Both have completely different approaches. Newton accused Leibniz of plagiarism and so on, and Newton made the Royal Society to ban Leibniz and so on. So people feel that as a result, the English British mathematics was left behind for many years. Anyway, it's a good, interesting, but the outcome of the works of Leibniz and Newton raised many doubts, raised many questions, and whenever you raise a doubt, trying to answer a question that proposes new ideas, brings out new ideas which are very good. So, for example, the concept of what is a real number, that became very prominent to analyze. What is a function, that was not known at that time. What is a function? How do you define a function? Nowadays, in our classrooms, we define a function as a correspondence between one set to another, and within 1 minute, the function is defined. It has taken a lot of time, and great mathematicians like Alembert, Bernoulli, and Laplace to debate and come to a conclusion, some sort of a conclusion, what is the concept of a function. And in turn, you see, this concept of a function arose because you wanted to define the areas and volumes, and a new concept, that function, was formalized out of it. So this is how things go side by side. And finally, it was the backbone of calculus, namely what is a concept of a limit. So these are the three fundamental things that mathematicians realize, that they have to understand, they have to formalize, they have to make it rigorous, so that more progress can be made on the ideas of calculus. So here is the pictures of Richard Dedekind and George Cantor. I would call their work as monumental work because this is philosophically great, and both had different approaches to these ideas, and they defined or they constructed real numbers as a complete ordered field. I don't have a time to go into what is complete ordered field. Basically, it's something like rational numbers that has the additional property of completeness that every monotonically increasing sequence bounded above is convergent. Right. So, so what is the concept of a sequence, limit of a sequence, completeness property, then limits of functions and continuity of functions. So now the modern classroom or modern study of calculus goes in this sequential order. So I will probably describe these concepts a bit. A sequence is a ordered collection of numbers. When you perform an experiment or you make an observation at different time points, you will get observations A1, A2, A3, and so on. So these are numbers and they're ordered. Okay, the first observation, second observation, and so on. So this is right. Like when we were trying in the method of Archimedes, when you draw a triangle, that is the first observation, the area of the triangle. When you double the sides, the area of the hexagon is the second observation, and so on. Okay, so one says that this AN's approach a limit L, okay, means that AN should come close to a value L. L is again a real number for all large values of that. Okay, so probably I think I will describe this so by writing. So here is A1, A2, A3, and so on. So on the side, you can keep your idea of the circle. So this is, so that is A1, that is area of the triangle. A2, you make it 6 sides or you make it a square. So you can make a square, that is A2, it's area of the square. So let us call A1 as the area of the square. And when you double the sides, you will get, so like this, you can double the sides. From square, you can go to, so this is inscribed square, inscribed octagon, and so on. So this is how sequence is generated. So A1, A2, A3, AN is a sequence, and you want to say AN converges to L, a real number. If the following happens, it should come closer to L. So how do you measure closeness of points in the real line? By absolute value. So AN minus L, that is the how far away AN is from L. Okay, and you want this small. So this is the error. L is the value they're coming closer to, and N is the actual observation, and this is the error, and you want to make that error small. For what numbers? Epsilon. So given any number epsilon bigger than 0, you should be able to find N. There exists some N naught such that this is N, this is less than epsilon for every N bigger than N naught. So if you keep this in mind, so the n-gons are filling more and more of the areas. So here is n-gons filling. So when you start with 3, okay, so you increase the number of sites 7, 8, 9, and you can see it's filling more and more of the areas. So, and so this is a monotonically increasing sequence. So and coming closer to a value L. So the completeness property of real numbers is if AN is monotonically increasing, bounded above it must converge. If you take the perspective of the line, here is A1, here is A2, here is AN, and all are, and they are bounded by something. They cannot go beyond this. There is a barrier. So what should happen? All these ANs must come closer to some value L. So that is what it says. So that is a completeness property of real numbers. So that is a convergence of sequences. So limit of a sequence becomes it can be defined. Okay, so every monotonically increasing sequence which is bounded above is convergent. That is the completeness property of real numbers. So the basic thing is making real number, defining real number properly with this property made the definition of pi rigorous as the limit of the n-gons. So this defined, this also can be used to find what is called the square root of 2. What is, we call it as a now Newton-Raphson method of finding the square root by sequences. I don't have time to go into this, so I'll skip that. So the applications of, now let us come to the idea of functions. We want to find out how to predict a value for a function at a point which may or may not be in its domain by analyzing its values at points in the domain but nearby point. So you are given a function f, right, and at a particular point c. Okay, I don't know whether the function is defined or not. I don't bother about it. Okay, but I know that f is defined at all points close to c. Howsoever close I choose a point to c, which f is defined, and I know what is the value of f of x at that point. From this data, I want to predict what could be a suitable value for the function at the point L. Okay, so what we are saying is take points close to C and look at the value f of x. If f of x is coming closer to L, then that is the value that we would like to predict for the function. Right. So let us this can be defined in another way, which is called epsilon delta method. So it says that this fx and L, they are close to each other. By how much close you want? You want the actual this to be equal, but this is the error you are making. So this error you can make it small. So how small? So that you should tell me. So given epsilon, you are able to find a point close to A by a distance delta. So given epsilon, there is a delta such that whenever x is close to A by a distance delta, fx is close to L by epsilon. So this is one way of looking at, if such a thing happens, you say f has a limit, right? Another way of which defining a limit is the following. So this is the point x is equal to c, and here is the function f of x. So you think this is the value that the function should take. Okay, so we want f of x to approach L as x approaches c. So another way of doing that would be, I can take a sequence. So let xn converge to c. Take a sequence, okay, xn which is converging to c, okay, and look at the image sequence f of xn. So that will be f of xn here, the image. So if f of xn's converge to L for every sequence, then we'll say L is the value the function should have. So then L is defined as the limit of f of x going to c. So there are two approaches to defining limit. One is via sequences, other is via epsilon delta method. The basic idea is coming closer. Okay, so f of x comes closer to L as xn comes closer to c for any way of that. So that is a way of defining. So probably I think let me go over. So f is a function, say defined in a domain I to R, and C is a point in R. C is a point in I, the domain I. Okay. Okay, let me, I just wanted everything to be available. So, right. C is a point in the domain. So I know what is f of C is given. But let us ignore it and let us look at what is the limit of x going to C f of C, f of x. So that is equal to L, say. So what is this limit? That is the value I expect the function to take by looking at its values at nearby point C. So if L is equal to f of C, if L is equal to f of C, you will say that f is continuous. So continuity should be taken as the actual value is what we expect by looking at the function at nearby points. That should be taken as continuity. So that is a way to understand continuity. So continuous functions, continuity of functions can be defined. So let me go over to this. So continuous functions are very important properties. One is called the intermediate value property, which says that if a function is continuous and it takes two values, and R is a value in between, f of A is one value at the point A, and f of B is another value at the point B, and take any point R, then this value must be taken by the function if it is continuous. So this is called the intermediate value property. So intermediate value property describes, right, continuity of the behavior of the function. And there are many ways of looking at this intermediate value property. If the domain is an interval, the range has to be an interval. Okay, that is another way of saying the intermediate value property. Because if the range is bifurcated into two parts, then there will be a point in between where the value will not be taken. So intermediate value property has many ways of saying image of a interval is an interval, and geometrically it says the graph of a continuous function cannot be broken. If you start drawing the graph of a continuous function, if you know it is continuous, then it cannot have a break in between. So that is what is called the intermediate value property. So limit helps you to define continuity, and continuity helps you to identify a feature of the function, namely that the graph cannot be broken. Right. So let us go over a bit more. So geometrically, it says that I have already described. So then there is a minimax theorem, which is also very important for continuous functions. It says if the domain of a, we have already said intermediate value properties is the images of intervals are intervals. But supposing the domain is a closed bounded interval. So can I say something more? Yes, you can say something more. If the domain is a closed bounded interval, then the function is bounded. That means the values, the range of the function cannot become very, very large, as large as you want. It should remain. So there is a m such that mod fx is less than or equal to m. And not only that, you can say something more. There are points C1 and C2 in the domain where the function attains its values. So C1 and C2, f of C1 is the maximum and f of C2 is the minimum. That is same as saying that the range of a closed bounded interval is again a closed bounded interval. This is part of the consequences of continuity. So let us go ahead. There is a fixed point theorem, a continuity of inverse function, and so on. Let us come to the derivative. which is a part of, normally we think calculus as derivative. So notion of derivative, the tangent line approximation, how derivative is used in increasing and decreasing functions, necessary conditions for a local maxima, local minima, Rolle's theorem and its generalization called Lagrange's mean value theorem, sufficient conditions for local maxima, minima, convexity and concavity of the function. So these are all topics that normally is done in differential calculus. You can think them as applications of differential calculus. So let me just briefly say the notion of derivative is precisely making the concept of drawing tangents precise, that namely the derivative of a function at a point is the slope of the tangent at that point. That you all learn. Many of the students make a mistake when you say what is derivative, they say it is tangent. Derivative does not give you the tangent, it only gives you the slope of the tangent at that point. And then the tangent line is very the tangent line. So if this is the graph of the function, and this is your tangent line at this point. So so this is the point C, and at C plus H, you can take this value on the line as the as an approximation. So f of C plus H can be approximated by this point, that is L of C plus H. That is a tangent line. Lx is the tangent line. So this is called the tangent line approximation. It's very important because f could be any function, weird function, but the tangent line is a linear function, so it gives you very good approximations. Right. So increasing, decreasing functions, for example, yeah. So let us look at two functions. One is going like this, and the other function is coming like this. So this is f, this is g. Now there is a categorical difference between the two. Both are continuous functions, but as you move from left to right, the function height is increasing. As you move from left to right, the function height of g is decreasing. So f is a increasing function, g is a decreasing function. Right. So can we say by looking at the function whether it is increasing or decreasing? Of course, one way is if you know the formula and you know the computations. So increasing means f of x1 is bigger than f of x2 if x1 is bigger than x2. That is the concept of increasing. But if you have some extra knowledge about the derivative, that if f dash x exists, if f dash of x exists and f dash of x is bigger than 0, then f is monotonically increasing. So extra knowledge about f gives you similarly about decreasing. So this is how calculus is used in analyzing increasing and decreasing. Another thing is, supposing f is a function. So let us say it's like this, f of x is a function, and this is a point C, okay, which is C is local maximum. C is a point of local maximum. If C is a point of local maximum, then and f dash of C exists, you know the derivative exists. So what should happen? It says this implies the derivative at C must be equal to 0. So this is a necessary condition. So keep in mind, if C has, then f dash of C is equal to 0. So this is a necessary condition. And all such theorems are very useful in analyzing maxima, minima of functions at points. Okay, but Okay, you already know there is a local maximum minimum. The question is whether given it could be local maxima, it could be local minima also. Okay, or it could be, but in general, given a function, for example, if I look at the function, say f of x is equal to x cube, and look at the graph of this function, so the graph will go like this, and it will go like this, and at this point, at origin, there is a derivative is equal to horizontal tangent is there. So that is only a necessary condition. It is not sufficient. Derivative equal to 0 does not say that the function will positively have local maxima or local minima at that point. So now one has to find sufficient conditions, and to find those sufficient conditions, a very important result in calculus is what is called Rolle's theorem or Lagrange's mean value theorem. So this is one of the important theorems which helps one to uh, uh, find tests for maxima and minima. And then these also go over further to devise tests for convexity and concavity of functions. So my idea of giving you a brief glimpse of all these things is that the notion of derivative involves the concept of limit. That is very important. Without limit, you cannot have derivative, and without derivative, you cannot have any one of these theorems. So limit is the backbone of differential calculus. So let me go a bit step further and spend some time on integral calculus. The notion of integral calculus comes because because one was trying to formalize the idea of area below the graph of the function. So the mathematicians who contributed in this, the first mathematician, of course, Riemann and Leibniz gave very intuitive ideas, but they were not rigorous, which were later on formalized by Cauchy and then by Riemann, and then a geometric interpretation of them was given by Darboux in 1875. So as a result of the work of all these, integral of every continuous function could be defined. Let me just indicate to you how the concept of limit enters into picture of this. So here is, let us look at the graph of a function. So this is A, this is B, and this is the graph of the function f of x. And what we want to do is we want to capture this area. We want to find an expression for this area. Let us call it as S. Obviously, we have no method of where to start. So the idea would be, as I said in the beginning, breaking into smaller parts and doing it. So let us break this interval AB into small parts. Call it x1, x2, and x3. So we have, I will start using the word partition. So here is, so what we'll do is we break this into the domain. F is a function from AB to R, and we have taken these points in between AB. So we call it as x4 and call it as x0. So now break it into smaller parts. That means what? So let us look at this interval, x1 to x2. Part of, in this is my function, right? Now, if I can find out the area below A to x1, area between x1 to x2, x2 to x3, I can add up those things and find out the area. right? So now let us try to see the x1 to x2. How do I find the area? I don't know what this function at present is. I may have a formula also, but that doesn't matter. But geometrically, it's quite clear that if I look at the smallest value of the function and look at this area, then the area below the graph of the function is going to be bigger than or equal to this area, the green one. And if I look at the largest value of the function, that is this, okay. So the value of the area below the graph of the function is going to be less than or equal to this blue area, right? So at least we have a handle now. We can approximate the area below x1, x2 by two areas which are areas of rectangles, and I can find those areas. So for example, this green one, right, is the minimum value of f of x in the interval x1 to x2. That is this height, okay, this height, okay, and into x1, x2 minus x1. So that is the area of the green one. So let us call it LPF. I'm saying lower because I'm taking the smaller value. Similarly, over the interval x1, x2, if I am doing it overall, so I should better be slightly more careful that if I want to add up all these areas, then let us add up all these areas and call that as LPF. And similarly, look at the maximum value. So this is the maximum value going up. Okay, that is the maximum value of fx in the interval x1 to x2 into x2 minus x1. So that I will call it as UPF. So the basic thing is that LPF is less than or equal to the required area, call it A, less than or equal to UPF. Okay. Now, but these are only approximations. How to make it finer and finer, better and better. The idea comes from adding more and more points in between. So the idea comes from take a sequence Pn of what is called refinement partitions. Look at LPN of F. Look at UPN of F. This one shows is a increasing sequence of numbers. This is a decreasing sequence of numbers, right? And both are bounded above and below, so they will converge. And if they converge to a common value, that is called the integral of f of x dx, and that is the area. So that is the basic idea of what I've explained is the idea of Darboux, and which was later on refined by Riemann. Actually, Darboux gave the work later on. Riemann came much earlier. Cauchy has given such an idea. The basic idea difference between the Riemann and Darboux's work is when you want to look at LPN and you want to look at maximum and minimum values, you have to assume functions to be bounded. Otherwise, you cannot define this minimum and maximum. For continuous functions, it does not matter much. Cauchy assumed function to be continuous. That's how he could define all these things. While Riemann, in his work, he said no need to take maximum and minimum. You can take any point and take that height and take the rectangle. Okay? So Riemann's work freed the integral from the concept of bounded functions, but there not every function was integrable. Some functions became integrable. And then those work went on to describe those functions which became integrable. So I think I have only time to describe. I won't go into all the properties of integrals, but let me describe what is called the fundamental theorem of calculus, and that is the theorem which brings the two theories together, differential and integral calculus together in one result. This was conceived by Riemann and earlier workers. They believed in this theorem, but nobody had a proof of that. Cauchy first gave a proof in 1873, and so here is the theorem. It says, let f be from an interval a b to r be a continuous function. So f is given to be continuous, and let us say capital F is another function from a b to r, and they satisfy this relation. Fy minus fx is integral x to y ft dt, where a is less than x is less than y less than b. So this relation holds if and only if there is I double f, this capital F is differentiable and its derivative is small f. The derivative of the integral is the integrand. So that is how this relates differential calculus with the integral calculus. What is the main crux of this theorem is the following. Let us take one way. Let us say the small f is the derivative, right? F dash is equal to f. So that means if I integrate the derivative, I'll get back the function. That is one way of the theorem. So you can recover the function by integrating the derivative. And the other way around says that if f is defined by this way, then f is differentiable and its derivative is the integral. And one calls that as capital F as the antiderivative of small f. So both the parts are captured in this fundamental theorem of calculus. It's one of the highlights of differential and integral calculus, combining the two. This is one of the theorems which troubles students very much, in the sense that as soon as differential calculus is known, every formula of differential calculus gives rise to a formula of integral calculus. So in the curriculum, as soon as differential calculus is over, students are asked to remember, I don't know how many, 500 formulas on integral calculus, and start doing computational problems. But the crux of the theorem, the fundamental theorem of calculus, is missed. So that is it gives a very easy way of computing the integral once you can recognize its antiderivative. So that is the advantage of calculation of different integrals becomes simple because of fundamental theorem of calculus. And another big advantage or big application of this is you can define what is called transcendental functions. If you remember, you start using log x, exponential x, sin x, cos x, trigonometric functions, and so on from very beginning of 8th, 9th, 10th, and so on, without bothering whether such functions exist or not. What are the definitions of such functions, right? Try to go back and think, what are the definitions of this? With whatever definition you take, can you prove the required properties? For example, log x is a function which is continuous, its derivative is 1 over x, it's 1 onto function, and so on. Or sin x, right? Between 0 to 2 pi is a 1 onto function which is differentiable with derivative, which we call it cos x. So these are some of the examples, applications of fundamental theorem of calculus. So I think I will stop sharing my screen and ask Soumya that in case you want to ask some questions, please put them in the chat box so that Soumya will be kind enough to pass on those questions to me, and then I'll be able to answer those questions, if possible, in the short time we have.
Yeah, so anyone has any questions?
You can unmute those participants.
Yeah, they can unmute.
Or they can unmute themselves?
Yeah.
Okay.
Yeah, Muhammad Iqbal, you want to say something?
Uh,
Hello, sir. May I speak?
yes, please go ahead.
Yeah, my name is Mohammed Iqbal. I have a question regarding the double derivative of a function.
Okay.
So, from my understanding, the point where the double derivative changes, I mean, where the function changes from convex to concave, or the other way around, is what is called a point of inflection, right?
Double derivative has nothing to do with point of inflection
So
or
can you please tell me what is the necessary and sufficient condition for a function to have a point of inflection?
necessary and sufficient. There are two different things. There is a necessary condition and there is a sufficient. There is
Yeah.
nothing called necessary and sufficient.
Okay.
Okay. And first of all, to define a function to be concave or convex, you don't need derivative at all.
Okay.
That is another misconcept that students or many of the teachers of teaching calculus have, that you can define convexity or concavity of a function only for. So let me probably go back to share my screen and say something. Okay, to answer your question will be best in case I share my screen and look at, yes. So let me look at what is a function called convex or concave. Okay, let me start asking you, look at the function y equal to x square, right? Are you there?
Yes, sir. Yes, sir. I'm here.
Yes. Do you think this function is convex or concave according to your definition?
As far as I'm concerned, it's curving upwards. So it's concave upwards throughout its entire domain.
So good enough. You're saying is concave upward. So
Yeah.
because you know that the derivative looks like this,
Yeah,
function looks like this.
Yeah.
But let me ask you, how do you think the function looks like this? This is a graph of y equal to x square. How do you know that? That is only after you have analyzed convexity or concavity of this function. Then
That's
you
true.
can say that the graph looks like this.
Yeah, that is right.
Okay. So this is because we have been told, we start believing. Okay. But so let us take this picture for time being to make you understand what is convex. So take any 2 points, x1 and x2.
Okay.
So here is the value x1. Here is the value, here is the value x2. F of x2. This is f of x1. Right?
Yeah.
Let's draw the segment joining these 2 points. This is a line segment joining these 2 points. Okay. Now, L is the line segment joining x1 and x2. What geometric observation, can you say something geometric by looking at this picture? About the segment and the graph of the function. Can you say something? Yes?
Not really. I mean,
Not really.
I don't see anything remarkable here.
Oh, don't see anything remarkable? Okay. So let me take another 2 points. Instead of this, let me take x1 here and x2 here. What is the value? This is the value. This is the value.
Yeah, right.
What will be the line segment? This is the line segment.
This will be the line segment. Yeah.
Now, can you compare these line segments and the graph and make some conclusion? At least in
lying
the
inside.
Yes?
Always lying inside the curve.
The line lies inside the curve. That's very good. One way of saying it. Slightly better will be that the line segment joining f of x1 with f of x2 never touches the graph of the function at any point. Never intersects other than those endpoints, wherever these points are.
Yeah, that is true. That is true.
that is the property of a convex function. And
Yeah,
that is
yeah.
a property I want to capture mathematically.
Yeah, absolutely right.
If
Yeah.
you want to give student a feeling, it is like a spoon lying inside a cup.
Yeah.
A spoon never touches the cup anywhere except at where the endpoints of the spoon are.
Yeah, yeah.
Okay. So how do I capture this? So the idea is between x1 and x2, if I take a point x in between here, I look at this is the value f of x. This is the value L of x. So f of x is always less than L of x. For every x1 less than or equal to x2 less than x less than x2. Is that okay?
Yeah, yeah. That's
So
true.
this is the property that defines what is a convex function. You don't need derivative at all.
Yeah, I understand, sir.
Now comes, if you have an extra knowledge about the derivative,
Mhm.
can you say something about the function without looking at the graph? I don't know the graph at all, right? For example, for y equal to x square, I know the derivative. I know the second derivative, right?
Yeah.
So let us analyze for this function, what is the derivative?
It's 2x.
Now, can you say anything about the function 2x? Nature of the function 2x?
Yeah, it's monotonically increasing.
Y dash equal to x is monotonically increasing?
2x, 2x. It's 2x, sir.
There's 2x, okay, doesn't matter. 2 doesn't change the thing at all.
Yeah, yeah.
So, it looks like for a convex function, the derivative should be increasing. It's a guess.
Not
It's
really.
It's a guess only, right? Do you think this is a valid guess by looking at it?
No.
No? 2x is not an increasing function. Do you think it is not increasing?
Yeah, it is increasing, but I don't think it's related to how we can approach
No.
a con.
No, I'm not saying approach. I'm saying that at least it gives
Yeah,
a
yeah.
hint that for this, for example, you look at y equal to 4x x to the power 4.
Yeah,
Okay.
yeah.
You look at again.
Yeah, that's true.
So probably this is the way at looking at examples, you should make a guess.
Yeah.
That is a theorem.
Mhm.
Says if f is monotonically increasing,
Mhm.
and if it is differentiable,
Mhm.
then the derivative should be bigger than 0 at all points. So this is the property of the function over an interval, not
Okay.
at a point. Limit, continuity, or derivative are properties of functions at a point.
Yeah.
They are local properties. Convexity, concavity is a global property, is a property on the line, on an interval.
Yes.
Okay.
Yes.
So this is how necessary conditions are obtained.
Okay.
So a necessary condition, we are saying if a function is convex, if the derivative exists, then it should be bigger than 0.
Okay.
Now you ask the question, is it sufficient? Okay. Then you ask the question, is it sufficient? And you prove theorems. So those are called tests of convexity and concavity.
Okay.
So I hope I have given you enough material to start looking at books and trying to understand what is convexity, what is concavity,
Yeah. Got
what
it,
are
sir.
necessary conditions, what are sufficient conditions.
Yes,
Every
yes.
necessary may not be sufficient. Every sufficient may not be necessary.
Yes.
Well,
Got it.
for this function, what is the first derivative? X4, 4x cube.
Yeah.
Is the second derivative? 4x square. At what point the second derivative is equal to 0?
0.
0.
Yeah.
And some of your theorem might say that because second derivative is 0, this must be a point of inflection.
Yeah, I got it. Yeah, understand. Yeah,
But x4 does not have a point of inflection.
yeah, that's true.
It is everywhere convex.
Yeah,
So every sufficient may not be necessary. So one has to separate out. Students don't understand these things. And many books also take definition of inflection point as second derivative equal to 0, which is not true always.
yeah.
Okay, fine. Somebody else has a question to ask?
Yes, sir.
Yeah, who is it?
Muzammil, sir.
Okay.
Sir, if we want to draw a graph of a function, then that function must be continuous.
Why? Why every human being should be beautiful and for everybody?
Right,
But
sir.
everybody can go to a photographer and get photographed, na? Camera doesn't say anything.
Yeah.
So
Okay.
does that answer your question, or you want something more?
Yeah, sir. So I want to imagine a graph where if x is rational, then
What?
if x is irrational, then f of x is equal to x. But when x is irrational, then f of x is equal to 0.
Good.
So how will I draw this graph, sir?
So how will you draw the graph?
Yeah,
Right?
it will be not solid line, no?
It will not be even a broken line.
Like dotted line, no?
It won't be a dotted line also, because whenever you put a dot, you don't know whether that dot is a rational or irrational. How do you know that?
Sir, we know the rational numbers, na? So we can put that dot.
You are only fooling yourself saying that if x is a rational number, then its value is equal to x itself or whatever. You'll put a dot there, right?
Yes.
If, but you don't know. For example, for y equal to x square, I know this is the picture. So here is a very important thing, that every function need not have a graph. Every function need not have a graph. That is the moral of the story. And that is what was looked up by a mathematician called Dirichlet. The example that you are giving is the example given by a German mathematician called by the name Dirichlet, who was a student of Fourier. He gave that example because till his time, everybody had that misconception that you had just now, that every function should have a graph. He said, look at, I'm giving you very simple. His example was much simpler. Look at a function whose at rationals the value is 0, irrationals the value is 1. Give me a graph of this function. And nobody could draw the graph. But he said, it's such a simple function. It only takes 2 values. So he said, you should not bother about graph is only a way of trying to understand a function. If a graph is possible, good. If not, you have to find other ways of looking at it. For example, let me give you a very scenario of modern day. You chat with somebody online. Who was it talking to?
Yeah, sir. Yeah.
Okay, so here is giving you a real life scenario. It's not a mathematical thing. You are chatting with somebody, you have an online friend, and you start asking the online friend various things. How do you look like? How and all, blah, 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 blah. And finally, you ask for a picture.
Yeah.
And the person says, I won't give you a picture.
Okay.
Then will you stop seeing that person or not? It doesn't matter, right? You will try to find some other ways of trying to find how does the person look like. Probably you have a common mutual friend. You will ask the mutual friend, hey, that person is not giving me the photograph. Can you say how does that person look like or something? Can you give me some hint or something? So when the graph of a function is not available, graph is the picture of a function, is a very big thing to have a graph. But if a graph is not available, you have to analyze it differently by different means. For example, the function that you are saying, that is a function which is discontinuous somewhere, right? And continuous
Yes.
somewhere. So by graph does not tell you anything about it, continuity or discontinuity. For some functions, you can look at the graph and decide continuity or differentiability. For this, you cannot. So you have to analyze analytically whether this function is continuous. If yes, what points, if discontinuous at what points, what kind of discontinuity it has, and so on.
Okay.
Yes, and I think we will take a last question. Somebody has, Soumya?
Yeah, I don't see anyone raising their hands.
Okay, so let me say that I am planning detailed lectures on calculus later on. So as and when I plan those lectures, I will be sending the mails to all those who registered for this. 249 people registered and only 19 are online now. Doesn't matter. So I'll be sending a mail. If you want to join those sessions later on, then do accordingly what is said. So all the best for calculus. Take care.
Thank you, sir.
Thank you, sir.
Thank you, sir.